Hi, you remember at the beginning of these videos, we talk about empirical molecular formulas. We say molecular formula shows you the actual number of atoms present in the molecule, but empirical formula only shows you the simplest ratio. And at the time I said, the question is, why do we even have empirical formulas? And at the time I tried to explain to you, well, empirical formula is a step in a step towards determining the molecular formulas. And pretty much this is what we're going to be doing in this video. We are going to see how to determine empirical formulas and then how from the empirical formula you determine the molecular formula. Before doing that, there's a couple of terms. Formula mass, well, that's the sum of the average atomic masses of all the atoms in here. When you have a covalent substance, no problem because you have a molecule. So formula mass and molecular mass pretty much are the same thing. Here you have an example, aspirin, C9H8O4. Carbon, you have 9 of them, each one weighs 12.01 MUs. Hydrogen, there's 8, each one weighs 1.008. Oxygen has 4, 16.00. Add up all of the numbers, so that gives you the formula mass or molecular mass. You can use either term of 108.15 MUs. With ionic compounds, we cannot do that because remember, they don't exist as molecules. They exist as crystals. So the formula mass is not the molecular mass. The formula mass is the weight of the basic unit of the crystal. Basically, that you look at what is the ratio of the ions, and whatever the simplest ratio is, that's your gives you the formula mass. Sodium chloride. Yes, sodium chloride can be huge. But if you look at the formula, and remember, it's not a molecule, okay? But if you look at the formula, it has one sodium that weighs 22.99, one chlorine that weighs 35.45. So the 58.44 MUs is the formula mass, but it's not the molecular mass because there's not a molecule, okay? Remember that. Another way we can express composition is percent composition. Pretty much you say what percentage by mass of each element you have. So they tell you have 10 grams of a compound and 2.5 grams are hydrogen, 7.5 grams are carbon. Well, the percent hydrogen is the weight of the hydrogen divided by the weight of the compound times 100. That's 25%. Percent carbon is the amount of carbon by the weight of, divided by the weight of the compound times 100, 75%. Sometimes you can just determine the percent composition if you know the formula. For instance, nobody has bothered to calculate in ammonia how many grams of nitrogen, how many grams of hydrogen. But we know the formula of ammonia, NH3. The formula mass is 17.03. So what is the percent nitrogen? There's one nitrogen atom, so you look at it in the periodic table, it's 14.01. There's 3 hydrogens plus the ammonia. This is the total weight times 100, so that's 82.27. Percent hydrogen, 3 hydrogens times the weight of 1 hydrogen divided by total weight times 100, 17.76. We were not given grams, but we had the formula, so we can determine percent composition that way too. So this is what we were leading to. Determine an empirical formula. You usually determine from the masses of the elements. Now, we determine from the masses because, once again, this is something that's done in the lab experimentally. So you're going to be weighing masses and you're going to have in grams. But when you make a formula, you're dealing with atoms or with moles, because a mole remembers a number of atoms. Okay? So the first thing, and this is critical, if you forget this, everything else will be wrong. Okay? But you have to change the masses to moles. How do you do that? Use the molar mass. Again, don't memorize, multiply, divide, anything like that. You have grams. If you put 1 mole, how many grams it is? Grams and grams cancels out, so that gives you moles. Now, once you have the number of moles, we want to see the ratio. So you do that by dividing each number of moles by the smallest number. That way, one of the numbers is going to be 1. And if you don't have whole numbers, you may have to multiply times a number to get whole number ratios. Many chemistry textbooks will tell you, if it ends up in this, you multiply times this. As I'm memorizing, if you have something that ends in 0.2, well, let me first add, if it ends in 0.9 or 0.1 as a round off, it's close enough. If it ends in 0.2, I'll multiply times 5. Why? Because that's going to be 0.0. You're going to get the whole number. If it's 0.3, I'm going to multiply times 3 because that gives me 0.9. And we say 0.9 is close enough. 0.4, you're going to have to deal with this one because it will be times 2.5. You may have to readjust, but again, that will give you 0.0. And so what I'm saying is that don't memorize what you do. Look at the example that you have and see what is the easiest way you can come up with either a whole number or a 0.9 or 0.1 that you can round off. So you have an example. This compound has 1.71 grams of carbon, 0.287 grams of hydrogen. First thing, change into moles. So you have the grams of carbon, that's the molar mass, grams and grams cancels out, so that gives you moles of carbon. Grams of hydrogen, molar mass, grams of hydrogen disappear, so you have moles. We say we divide by the smallest. Which one is the smallest? 0.142. So when you divide them, you end up, this is 1, carbon 1, but we don't represent it. This is actually 2, CH2. That's the empirical formula. That's easy. But please, please, please do not divide grams by the smallest number. Change it to moles. That's what so many students forget. There was a time I was teaching at accounting, and I actually dressed like a cheerleader. And I had made a little dance. There was a couple of attention cheerleaders in my class, and they helped me about changing to moles. And I actually showed up the day of the exam, dressed like a cheerleader, and I went into the room where they were taking the exam. They had all of the chemistry students, so my students were scattered throughout different rooms. And I went into every room and I did a little dance, change it to moles, change it to moles, change it to moles, go to the next room, change it to moles, change it to moles. Just to make sure everybody remember, you change grams to moles. If you don't learn anything else in chemistry with me, you learn to change to moles. This particular example, they give you grams. The same thing they already did steps 1 and 2. So you have moles, but this time, we come up with 3.5. We want whole numbers. Oh, that's easy, because if you multiply times 2, then you get a whole number. 3.5. If I multiply times 3, times 4, always the smallest number, that's going to be 7. That's a whole number. Always begin times 1, times 2, times 3. Because if you multiply times 4, you still get a whole number, but that's not the correct answer. So you begin 2. Now, this doesn't say, but you know that's a 1. So you have 2 chlorines and 7 oxygens. That is your empirical formula. So basically, they say, take the mass, change it to moles. And I said, don't worry about that. Don't memorize multiply or divide, because that's what causes a lot of trouble. You use, since you're changing grams to moles, you want to get rid of the grams, so you put 1 mole, however many grams. Now divide by the smallest number, and if necessary, make sure that they're whole numbers. But sometimes it comes out right from the beginning, sometimes you don't need it. Okay, this is pretty much the steps. Change it to moles, divide by the lowest number of moles. If necessary, make sure that the numbers are whole numbers, small whole numbers. End of the story. Sometimes they give you percent composition instead of grams. And I remember the first time I put one of those problems in an exam, like almost everybody in the class missed it. And it's like, I can't understand, there's nothing wrong with the question. If I'm telling you that my molecule has 25% of one atom and 75% of the other atom, let's assume that your sample is 100 grams. Then that means you have 25 grams of A and 75 grams of B, sorry. You could assume the sample is any mass that you want to, because you're going to be looking at the ratio. It doesn't matter. I just say use 100 because that makes automatically, you know, the number of grams. All you're doing is changing percent with grams. You want to say that your sample is 214.67 grams? You can do that and calculate how much is 25% and 75% of that. Why you do that? It's easy to just change percent. Now, once you have grams, you do the same thing, change into moles, divided by the smallest number. If necessary, make sure you get the whole number ratio. The only difference between the previous problem and this one is that they gave you percentage and you automatically deleted the percentage and put grams. That's all. People think that this is difficult and really it's not. Here you have an example, they give you percentage. Okay, notice that they don't even waste the time. They write as grams. Then using the molar masses, they change it to moles. Divided by the smallest one, they had empirical formula. You didn't do any extra steps because when you were writing down the numbers, you automatically change percentage by grams. That's the only difference. Percentage or grams. You automatically change that exactly like the previous problem. That's why I couldn't understand how a whole class, I usually don't worry too much when students miss a question, but when a whole class misses a question, it does make me go back and say, is something wrong with the question? No, there's nothing wrong with the question. It's just students freaking out. There's no other explanation for that. Just in case I decide to include a comment on that, so it won't happen again. Now, how do people determine number of grams? The most common form of doing that is combustion analysis. And that's used a lot with hydrocarbons, because if you have many inorganic molecules, it becomes too complicated. But we're just going to study this technique. Okay? Basically, what you do is you put your sample, you heat at a very high temperature while adding oxygen, so it burns completely. And what does it produce? It produces carbon dioxide, water vapor, and sometimes some hydrocarbons have a couple of other things, so you have other products. But in general, that's what you produce, carbon dioxide and water vapor. If you can isolate, I'm going to show you how, the carbon dioxide and weight, and isolate the water vapor and weight, then you can from there determine the number of grams or number of moles of carbon, hydrogen, and oxygen. So we're going to be looking how you do that. This is the system. You have a furnace, you put your sample, blow oxygen, so you produce carbon dioxide, water, there's excess oxygen, and sometimes there's other gases. The excess oxygen and the other gases come out. They go through a tube that absorbs water. So if you had the weight after it has absorbed water minus the weight before you begin, that will give you the weight of water. The same thing in this one is going to absorb carbon dioxide. So the weight after the experiment minus the weight before gives you the weight of carbon dioxide. So that's what is going to be given to you. They give you so many grams of carbon dioxide, so many grams of water, and from there, we are going to see how you work these problems. So here you have an example, polyethylene. Okay, just produce storage bags and many things. So under combustion analysis, you get so many grams that's your initial sample, so many grams of carbon dioxide, so many grams of water. And we know polyethylene, they usually tell you that it doesn't have oxygen or that it's made up only of carbon and hydrogen. Here they're just assuming because they call it hydrocarbon that you know what they're talking. But I promise in the exams it's always given. So what is empirical formula of polyethylene? You have to change the grams of carbon dioxide to moles, the grams of water to moles, and now you say, okay, one carbon dioxide has one carbon, so you can calculate the moles of carbon. One water molecule has two hydrogen atoms, so you calculate the moles of hydrogen. Once again, once you have the number of moles, divide by the smallest number, blah, blah, blah. So let's do the example. Carbon dioxide, we change it to moles. So we have moles of carbon dioxide. There's one mole of carbon, and 1 mole of carbon dioxide. So that gives me how many moles of carbon. Grams of water, I change it to moles, but I know water is H2O, so there's 2 moles of hydrogen in each mole of water, so we calculate the moles of hydrogen. Like I said, divide now by the smallest number, give you 2-to-1 ratio, so this is the empirical formula of polyethylene. When you only have carbon and hydrogen, it's as easy as it can be. The problem is when there's oxygen, and let me go back to the furnace, you're adding oxygen. So not all of the oxygen that you have in there comes from the sample. Some of the oxygen is going to appear as carbon dioxide, some is going to be as oxygen, some still comes out as oxygen gas. So how do you know how much of the oxygen goes into carbon dioxide, into water, how much of the oxygen was in the sample, how much is given? You can't. Okay, so you're going to have to go through an extra step. And let me give you an example. So you have this sample in here, and it produces this carbon dioxide in this water. And it tells you it contains carbon, hydrogen, and oxygen. So you say, they gave me a problem with oxygen. Well, you're only adding a little step, okay? So first you get the grams and calculate moles of carbon dioxide and moles of water. From the moles of carbon dioxide, you determine the moles of carbon. Remember when you calculate moles of hydrogen that you have 2 hydrogens per, so you have to multiply times 2. So now the question is, how about the oxygen? Well, if your compound only has carbon, hydrogen, and oxygen, the weight of, let me call it carbon, hydrogen, and oxygen, minus the weight of the carbon, minus the weight of the hydrogen, is going to give you the weight of the oxygen, right? So, how many grams of carbon? You know the moles, so you change moles of carbon to grams. The same thing with hydrogen. The moles of hydrogen, you change it to grams. They give you the weight of the whole sample. So the weight of the sample minus the weight of the carbon and hydrogen, that tells you how many grams of oxygen, which you can change to moles now. So we know how many moles of carbon, how many moles of hydrogen, how many moles of oxygen. You do like we've been doing up until now, divide by the smallest number, make sure you have the whole number ratios. That is your empirical formula. So the only problem is determine the moles of oxygen. So first you need to determine grams of oxygen, and you determine them, like I said, by subtracting from the weight of the sample, the weight of the carbon, and the weight of the hydrogen. And now when you have grams, you need to know how many moles of oxygen, sorry, just oxygen atom. So once you have all of the number of atoms, it's just the same old problem. You added one step to determine the moles of oxygen. That's it. It's a little bit longer, but just as easy as the previous one. Now, once you have the empirical formula, how do you calculate the molecular formula? I like to ask my students. Imagine I come to class carrying a box, I can hardly carry it, and I dump it on the table. So you won't believe it, but I weigh this box in my office, and it weighs 24 pounds, and it's full of chemistry books. Out of curiosity, I weigh one book, and one book was 2 pounds. So how many books do I have in the box? And everybody knows I weigh 12. How do you know? Because 12 books times 2 pounds give you 25 pounds. Exactly. Now, a molecular formula can be equal to the empirical formula or can be multiple. Remember the example that we saw, like glucose, C6H12O6, the empirical was CH2O. Or carbon dioxide can be the real formula and it can be the empirical formula. So basically what you're saying is that the empirical formula can have, the molecular formula can have 1, 2, 3, 4 empirical formulas. And it's up to you to determine that number. So if you divide the molecular mass by the mass of the empirical formula that you just calculated, that tells you how many empirical formulas you have in there. In this particular case, you say that there is 6 empirical formulas. So just multiply any subscript times 6. Let's do an example. Okay. Actually, I didn't realize I was using glucose in here. But this is the empirical formula, and you can calculate that it weighs 30 MUs, again, because you look up the weights in the periodic table. They tell you the molecular mass is 180. So 180 divided by 30, that tells you have 6 formula units. You have the empirical formula times 6, or C6, H2 times 6, 12, or 6. So the molecular formula is this. Be very careful when you're doing problems, especially in an exam. Are they asking you for the empirical formula or the molecular formula or both? Read the questions, answer everything they ask you, but don't add extras. If all they want is the empirical formula, don't waste time. Sometimes they will give you the mass. That doesn't mean they want you automatically to calculate the molecular formula. You realize in chemistry sometimes they give you information you don't need. Answer everything they ask you and only what they ask you. That's the secret to success in chemistry. So once again, I have a worksheet practicing combustion analysis, determination of empirical and molecular formulas. In the video description, there's a link to my Wasant account. You can make an appointment with me. We can go over this and I can give you my worksheet. So remember, practice makes perfect. So let's practice.